All right, let's get started. So today I think is fun because we get to do stuff on graphs, and that means there's more pictures. Uh, and then yeah, so we're gonna do. Actually, next three will be about graphs, but the third of those three will be doing dynamic programming on graphs, so to speak. So somewhere in between. So okay, so today's about searching and sorting graphs. The topics we'll cover. I don't know if this is very helpful. You might have seen some of these terms before. You probably have seen them at least before. Things like acyclic graph, topological sort, whatever. But let's get into it. So, uh, presumably you've all seen graphs before, but I probably shouldn't skip this slide. So there's these objects. Well, you've already had homework with graphs, but you have vertices. There are these points, and you have edges connecting them, right? So you're kind of mapping or describing these discrete relationships. We have two kinds of edges. One is an undirected edge, so to speak, and then the other is a directed edge. So it all just depends on the problem, which one you want to use to model. But this usually, you know, describes some kind of mutual thing like friendships or something like this. And then directed is, more like one-way connections, like internet links, right? A link goes from point A to point B, but not necessarily back. So, okay, so that's just like, a nice way to model the world. It's very useful. I'll go through this part quickly because it's not too exciting. But there's still a basic point of like, how do you even represent a graph in a computer? Right? Like if you want to just make the vertices and edge information accessible and useful, you want to store it and structure it somehow, right? Maybe you've already done this before. What are some ways to structure a graph in your computer, organize or represent it? Interesting answer. Other answers, yeah. Okay, so an adjacency list. Hopefully that's the first one. I never know. Good. Okay, so an adjacency list will just list for each vertex like it's out neighbors. It's a directed graph, maybe, oh, I can go here, 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 just in the list. And then you could, if you want, also have the in neighbors, from here, 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 here can reach me. Okay, so just a linked list of all the neighbors, maybe directed. Okay, so that's one. What's the other one? Adjacency matrix, something like this. So here I imagine like a big table, one row for every vertex, one column for every vertex. And if I look at like row U, column V, I'll put like a 1 there if there's an edge from U to V. Otherwise, I'll put a 0 there. Sometimes we'll have edge lengths. Today, we won't have edge lengths. Then you might put the value of the edge there. Okay, that's simple enough. Okay, there's some trade-offs. For example, what is one advantage of the adjacency list? Partly just to make sure we're on the same page. Potentially less space. So if you have, a graph can have up to n squared edges if you have an edge between every pair of vertices. But the adjacency list only lists out every edge. So if you have, much less than n squared edges, this may take much less space. What would be an advantage of the adjacency matrix? Less time. Yeah, so less time in particular for. Yeah, if I just want to know if there's an edge from U to V, it's just a direct lookup here. Whereas there, I might have to like scan a list or something like this. Okay. If you wanted the best of both worlds, what could you do? The best of both worlds? I don't know. Oh, I would say maybe one thing also nice about adjacency list is you can more efficiently list out all the neighbors because you skip all the zeros. That's also nice. Now, suppose I wanted both of those features. I wanted to be able to look things up, is there or is there not really fast? And I also wanted to be able to list all the neighbors of a vertex very fast. How can I get both? Yeah. Huh? Edge list? Well, that's sort of like part one, right? Yeah. You could just use both. Okay, you can have both. It's just a trick question. Anyway. I think for the most part, we can just take for granted, like looking up an edge and whether there's an edge, and that's not too interesting. But it's still good to take one moment to think about, okay, how you would actually represent it in a computer. Okay, so today we'll talk about three things, and you've probably seen some of this stuff before. Maybe you've seen depth first search before. At least that rings a bell. Okay. So we'll look at it very closely. I don't know how it'll match your background, but we'll look at something called directed acyclic graphs, and then we'll talk about DFS, and then we'll do something about using DFS to structure the graph in an interesting way. So maybe you've seen this before. A directed acyclic graph is basically as defined. So here's a directed graph. Here I've drawn all the edges going from left to right. And there's no directed cycle. So a cycle is when you start in one place, you walk around, and you come back. Okay? So that's a DAG. Maybe you've all seen DAGs before. A vertex that doesn't have anything incoming, like those two vertices on the left, that's called a source. A vertex with nothing outgoing is called a sink. Okay. I claim that every DAG will have at least one source. Why? Yeah.
You need a starting node.
Because what?
You need a starting node.
Yeah, why do you need a starting node though? It is a starting node. I mean, at some level, a source is a starting node. So why do you need a starting node? Yeah.
If you don't have a starting node, then it would be a cycle.
Yeah, some level it'll be a cycle. I mean, here's another way. So pick any vertex to start with. If it's not a source, okay, it has some incoming edge, right? And if this is not a source, it has some incoming edge. And go on and on and on and on. By the time you've visited n+1 times, you would have to repeat a vertex and you'd have a cycle. Okay, so if this went on indefinitely, then you'll stumble into a cycle. That's just kind of making explicit, I think, what you all had in mind. For the same reason, you can argue there's always a sink. Pick a vertex. If it's a sink, you're happy. If it's not, you can go somewhere else. You can go somewhere else. You can only do that so many times without being forced to repeat a vertex, but you shouldn't be able to repeat if there's no cycles. Okay, so there's always a source, there's always a sink. There could, of course, be more than one. Good. A canonical example of directed acyclic graphs is like a circuit. Okay, so here's two circuits representing some whatever Boolean thing, right? But the idea is, maybe you put true here and false here. These are Boolean variables, and they propagate through the circuit following Boolean logic, right? So this true goes up here and it becomes a false. This false goes up here, it becomes a true, right? You can kind of propagate up through the graph. And here you have, if I was looking here, you'd have true or true. So that would be like true. And I guess if you're looking here, you would get false or false. So you would get false. And then finally, this would evaluate to false. Okay. But if you want a circuit where like the values feed forward, then you don't want any cycles, right? You shouldn't somehow be recomputing. It wouldn't be, if there was a cycle, it wouldn't even be clear how to evaluate the circuit. Okay, so circuits often are naturally acyclic. Right. That's okay. Yeah, okay, so this is just breaking it down a little bit more. You have these binary input gates. This is taking the logical or, true or false is true. This is taking the logical and, true and false is false, right? You all know this stuff. Okay, so that's just an example. Okay, so here's maybe a, oh man, well, I kind of blew it. Oh well. So how would you evaluate a circuit? Well, as drawn here, you would evaluate it bottom up, right? You kind of want all the inputs ready so that you can evaluate that next node, right? So if I had x1, x2, x3, x4, then I would just look up and be like, okay, I have all the inputs I need to evaluate this or, I have all the inputs I need to evaluate this and so on and so forth, right? You can't evaluate a gate until it has its input. That'll naturally kind of send you from bottom to up. So, all right, I think nothing too special. Now, with that in mind, we can define a topological order. Okay, so I can think of these arrows as representing some kind of precedence, right? Oh, you need this input before you can evaluate that output. Okay, so if every arrow I interpret as a less than equal, then you'll get what's called, a partial order. Okay? There won't be any contradictions because there's no cycles, but some things are incomparable, right? There's no clear precedence between x1 and x3. I don't know which one would come first. At some level, it doesn't matter. Okay, but You can still do transitive things like, x1 is less than that or above it, which is less than that and above that. Okay. So, all right. So here's our first interactive moment of the day, or second. We're going to, let's list off, just to make sure we're on the same page, all the nodes in kind of from smallest to biggest within this partial order. Smallest to biggest is not perfectly well defined. Okay, but we're just going to go in increasing order from left to right. Okay, so you just shout out like some vague description of a node, and I'll put 1, and then I'll put 2, and I'll put 3, and then we'll number them all off. And then we'll make sure we're all on the same page. Sounds good? All right. What comes first? X1, okay. Next? X2, okay, next? Next? X4, okay. All right, now we have some decisions. What comes next? There's many right answers at each stage usually.
4x.
Okay, this one here, this OR. Okay, next.
And right next to it.
And next to it, and then. All right, this not maybe. Not. All right, I'll just keep going. And not, or, and something like this, right? So you can number them off. And I think that our numbering, this is one possible numbering, but it should agree with all the arrows. Okay, we should never have like a number that's less than another if the arrows go in the opposite direction. Okay. So, right, so this is called a topological ordering. It's any total ordering of the nodes that's consistent with all the edges. Right? It's not necessarily unique. We could have reversed x1 and x2, so on and so forth. And I guess drawn out, it'll be something like this. But one thing nice, right? If you had a black box that took a DAG and gave you a topological ordering, you can just run it, and then you can just evaluate your circuit from left to right. Right? So you don't have to write code that's like keeping track of how many neighbors do I have left? Do I have all the inputs? You can imagine writing some code to evaluate a circuit and getting kind of detailed. But if you had a black box that just compute a topological ordering to give you some kind of numbering that's consistent with the edges, then you can just run through from left to right. It's one loop. I'm here, I just look back. It's very easy. Okay? So it's a nice thing to have. Okay. So maybe I should, yeah. Does anyone want to propose an algorithm for computing a topological ordering that didn't look too closely at what I just showed? If we wanted to do this automatically, of course, if you look at something as small as this and I have a pen in my hand, I can number them off. But how would I actually describe an algorithm? As sort of a graph algorithm, yeah. Okay. Yeah, so we can remove nodes within degree 0. So if we did that here, we would be removing x1, then x2, x3, x4. And as we also delete these edges, that opens up more sources, right? So if we did that here, right, we could remove this source and all its edges. That's one down. Remove this source and all its edges. The original sources are gone, but new ones are available. It's still a DAG. Every DAG will have at least one source. You can remove this one and its edges, remove this one and its edges, and gradually we're clearly chewing away at the whole graph. Imagining I'm actually spitting out the labels as we go along, right? Remove that one, remove that one, remove that one, remove that one, and then you're done. Okay, so in the language of graphs, it's just keep finding something within degree 0, keep finding a source, keep ripping it out of the graph, updating the adjacency list to kind of delete some things, and you're done. Okay. So that would be, okay. Right, so yeah, you might end up spitting something out like this. I think this is actually accurate, partly because one student actually looked very closely and some previous version found an issue. But anyway. Okay, so that sort of describes an algorithm. Well, there's a source V, maybe I output V, and I remove V and all its incident edges from the graph. Okay. How long would it take to run this algorithm? Or maybe how can I run it fast? Something in that ballpark. Yeah.
If you have some sort of like min heap where like you have the lowest in degree at the top, that you just take off the top one. Right? So it'll be all of it.
So here you're looking for the min degree thing, right? So each iteration you want to find the min degree vertex. How long does it take? So you said n plus n overall. How long does it take to use a heap? How much does a heap operation take? Log n. So I think actually this might not quite be m plus n because each time we remove a vertex, you're paying log n. You might also be paying when you update the heap depending on your heap. Okay. But this is actually m plus n log n at the very least if you're paying log n to remove the minimum degree vertex. Can anyone do better? Yeah.
Do an m plus n, just do one task first, get the in degrees that are 0, and then when you recurse or like that list, whenever you delete a node, you can remove the in degree of the recurse and then add that list of it.
Yeah, so here we have even more structure because you know what the min is that you're kind of looking for, so to speak. So if you just kept track of the in degrees of all the vertices, maybe first you just go through and you count up the edges. Oh, this has in degree 5 to start, that has in degree 3 to start. Then as you go through, you remove a vertex, you delete those edges, and then you update those counts. Oh, this vertex lost an edge, that vertex lost an edge, that vertex lost an edge. So each time you delete an edge, you also update one counter. So it's a one-to-one thing. It's not really much overhead. And then you just have to keep track of which counts reach 0. Some count goes down to 0, you just attend it, put it on your list. This one's a source. So this one you can actually just do it directly without really a data structure in some ways. That'll get you down to m plus n. Okay. So this very simple removing sources, with just a little bit of care to track the in degrees as you go along, that'll give you a linear time algorithm to compute a topological ordering, which is pretty intuitive, right? I'm pretty sure when you were evaluating that circuit, this is what you did in your head. You just kept removing sources. Okay, good. All right, so that's part 1 down. I don't know if you've already seen all that before, but on to part 2. Okay, so searching graphs. I guess here was supposed to be an example of a graph. This is obviously a picture of Lawson, and there's, streets look like edges, and this is how you get from Lawson to here. I think this map is misleading because I feel like once you get into building, that's when like it really begins. Anyway. Okay, this one's fun. Okay, so this is roughly the kind of problem we're going to be solving. Okay, so this is a maze of cats. So here's the rules. So you see like all these cats, right? And you're going to start at the starting cat in the top left, and you're trying to get to this white cat in the bottom right. Oh no, that's backwards. That's the goal. Oh, that's the goal. So that's where you end, right? And you have to alternate cats. So you have a cat facing you, and then you go to an adjacent cat that's not facing you, cat that's facing you. Okay, so the goal is to either get from start to finish or conclude that there's no way to get from start to finish. I'll give you a chance to look at it. Yeah.
Unless I like miscounted something, I don't think you could, because if you go from the goal backwards, it ends up being blocked off at every stage.
So is everyone else stuck? So let me retrace your thoughts. So you're saying if you started here at the last cat,
Yeah.
that looks kind of bloody, but oh well. And you went backwards to here. You can only go to the left, and you can only go up,
And then you only go up again.
and you only go up again.
And then you can go to the right
Yeah, it felt like those were kind of forced, huh? Is this where everyone else concluded? Yeah. Yeah.
The last like blue cap that you stopped at, you could go left. There's a giant blue cap next to the background color in the middle.
Okay. So maybe from here you can go here,
And then there's a front facing tab on the left.
and then here. Sorry, I don't mean to put bloody bullet holes in every cat. So I guess from here it's okay, maybe. Okay. All right. So yeah, there's the implicit cat. Yeah. Right in the middle. Okay. Gets them every time. It has no eyes. But it's the backwards cat, yeah. Yeah. Question? Issues? Every once in a while there's a student who's quite upset about this, but I guess you're all okay with it. Okay. Anyway, so at some level we want to do this automatically. I guess computers don't have this issue because they have these adjacency matrices and stuff. All right, so that's the cat maze. All right, here's another one. This time there's no ambiguity about cats. But it's a natural question to ask, given a graph, right? Here's some starting vertex S. Can S reach every other vertex in the graph? I guess I can take a vote. Now, some people are still looking, so no rush. All right, ready to vote? Okay, so first of all, who's not voting? One. Okay. All right, who thinks that S can reach everyone? Okay, I'll put that at like 9%. Okay, and then who doesn't think it can reach everyone? That's most of you. Okay. Okay. Well, very honest. Okay. A lot of you said no. So who can you not reach? Yeah.
Point directly below us.
The point directly below S. That's right. So there's this triangle in the middle that actually you can't get to. None of the edges are going into that triangle. But it might be hard to notice because there are some edges going into each of those vertices along that cycle. Okay. So these are relatively modest examples, right? There's like, I don't know, 10 nodes up here, and it still requires like staring at quite a bit to answer a kind of simple question, right? So these algorithms are kind of non-trivial, even if we have good solutions. So our goal, of course, is to design an algorithm that figures this out automatically. Yeah, this is a very practical thing to do. Like if you're doing garbage collection, right? You have all these objects pointing to each other in memory, and you have some objects on your stack. These are the things your program can actually access. So if you did reachability from there, you'll figure out all the stuff you will never get used by your program. You can recollect memory, right? That would be an example. Okay, good. So, right, so I think, when we look at these kind of mazes and map problems and stuff like this is just a small point. We often think of like having this very nice bird's eye point of view, right? And I just want to point out that I feel like as far as a computer can tell, a computer is just kind of like nosing around and just making one observation at a time. So I always feel like a computer, the way it works, is a little bit more like working at the street level, gradually exploring the graph as it goes along, right? It doesn't have this clear point of view. Like graphs in your program don't look, like something on image. It's like being in a maze compared to just seeing it from up above. But okay, so much for that. All right, so I know that at some level you know what the answer to this is, but just work with me. Let's try to come up with an algorithm to solve this problem from first principles. Okay? So I thought that now first we can at least try kind of our, the recursive thing we've always been doing, see how far it gets us, and figure out how to make certain adjustments. So if I wanted to write like a recursive algorithm, and I want to figure out if S can reach T, then I might just start with a sentence like recursive search ST, and then I just have to fill it in. Anyone want to fill it in? Anyone willing to fill it in? Yeah.
Determines if S can reach T.
Yeah, determines if S can reach T. Let me just make that a little more like explicit in terms of input output. I'll just say true if S can reach T and false otherwise, just to make very clear what we mean by determine. Okay, and if I was going to implement this as a recursive algorithm, just like a naive recursive algorithm, what might we write? Yeah.
Base case would be if S equals T to return true.
Uh-huh. Otherwise,
Otherwise, you loop over S's children and you make a recursive call for each one of S's children. If there's no children, then you just loop over this.
yeah, so maybe for all outgoing edges SV, if, so I have S and I'm exploring all the out children and I'm looking at some vertex V. If I recurse and I find out that V can reach T, then I can go from S to V to T. So I can return true. And you only need one child, or one neighbor to get you there. So you can just return right away. Otherwise, if you exhaust all the edges and you don't find any way to get there, then okay, you conclude it's impossible. Okay, so something like this is very simple thing, and based on week 0, I think this is the most natural thing to try to do. So good. Now, okay, yeah, continue to work with me. If I was going to argue this algorithm worked, what would be like? Why would we work? Why would it work? What's like the natural line of thinking? Yeah.
You're eventually going to traverse all the paths that S can essentially make, and if it doesn't hit T, then we know that through any of those paths it can't find T.
Yeah, is it gonna traverse all the paths that leave S? Yeah, I mean that's definitely true. Somehow, yeah, I'm trying to figure out how to make that even like more explicit, I guess. It feels like a little bit of a leap to just say that you're gonna traverse all the paths.
S we could go to like anywhere that can't go to T to like this.
Yeah, so here's what I wrote. So first, if S is equal to, that's not right. Okay, if S is equal to T, you're okay. Like our base case is okay. If S can reach T and S is not already T, then, there must be some path to T, right? And there's some next vertex on that path that's also a neighbor of S, and that algorithm will try it out. That seems like a completely plausible argument, right? And in particular, at this point, we can say by induction or recursively, maybe, recursive VT will return true. Yeah.
Isn't this technically not correct though? Because if you have a cycle, then you can.
Yeah. These are perfect. So this is a flawed algorithm because of course, in a simple situation like this, our algorithm will go around and around and around and around and around. But I only wanted to make this point because this looks almost like something that I've encouraged us to do for 2.5 straight weeks. So what went wrong? What's flawed about this? This almost sounds like the vibes are good. Like some AI slop here. It sounds like something I'm looking for in a solution. But of course it is broken. Yeah.
Is the size on smaller?
Yeah, so we're not really making any inductive step here. The input didn't go down, right? So it's not like we're working on anything smaller. and things like this. So this sentence here, recursive search VT returns true, that's making sort of a leap that's not quite there. It is true that sentence-wise, like if V can reach T, then S can reach T. That is true. But in terms of the algorithm, yeah, okay, so at some level, our goal is to sort of figure out how, to work our way out of this. Okay. All right, so recursion requires induction to be correct. We're not actually generating smaller inputs on our recursive calls. So that's, one point that breaks compared to what we've been doing for the past few weeks. All right, how can you fix this? Maybe you already know the answer, but yeah.
You just keep a list of all of the nodes and then subtract whatever nodes we visited.
Yeah, so marking. So we're going to use memory. In some ways, that's sort of similar to dynamic programming. But at some level, if you're doing a maze, right, it's much easier to do a maze with pen and pencil than without, right? If you actually trace what you've already visited, then it's much easier. Okay, so if we can actually use memory and mark places as we go along so we don't visit the same place twice, it's almost like not solving the same problem twice, then actually we can make some progress and get something a bit faster. So, okay, so I assume everyone has seen this before or heard of this depth first search. Okay, so the only difference from the recursive algorithm is these two steps. When I enter a vertex, I first check to see if it's marked. If it's marked, I just exit right away. If it's unmarked, then I mark it and then I start searching. Okay. So for example, if I was starting here, right, and I ran it from here, the algorithm would go like here. So you would mark this right away. It would go here. It would mark it. It would go here. It would mark it. Now there's no children left. You back out. It would go down here. Maybe my circles will be marks. Okay. You mark it. You go down here. You mark it. Now there's nowhere to go. You back out. You go over here. You mark it. You go over here. You mark it. Go over here. You mark it. You go all the way down here. You mark it. And now I think there's no children left, so you have to back out. Back out. Also, correct me if I missed something. I'm a poor computer. You back out. You back out. You back out. I think you back out to here. Now you're back at S, but you're not done searching S yet. You've only explored one of its neighbors. Maybe you go this way. You mark this one. You go over here. You find the vertex has already been marked. So you don't explore further. You just back out right away. Maybe you go here. This is unmarked, so now there's more work to do. You go here. You find it's already marked, so you back out. There's no more neighbors left. You back out. You back out. And I think at this point you conclude I've visited all the neighbors and I've marked what I can. And then we see what's left over are those three unreachable vertices, and exactly those three. Okay, so you just go in, you mark, you back out. I think it's very intuitive. I'm guessing you've seen it all before. Okay, good. So what I want to focus on is just proving a couple of basic but somewhat rigorous claims about depth first search, particularly because we're going to use it as a subroutine afterwards. Okay, so two claims. I think one is easier than the other. One is that it's going to run in linear time, which you all probably knew. And the other is that I want to prove that if I start at a vertex V, it will really visit all the vertices at V, reachable from V, which I'm sure you all intuit and believe. So this is more an exercise of let's try to get it down cleanly, put ideas into words. All right, so the first one is the running time. Anyone want to justify the running time? The claim is that it takes linear time, looking at the edges a few times, looking at the vertices a few times. Yeah.
For every node that you hit, you will do an amount of work equal to its edges, and you can just kind of think of each node as being like its own problem. And so you're going to do operations for the number of edges plus some marking for the number of nodes.
Yeah, so for every edge or for every vertex you hit, you're going to look at its edges or something, right? So just for this, let's just replace the word hit with something that appears in the language or in the program. So maybe I might write something like, again, I think this is all stuff we understand. It's just an exercise in, how can you describe it cleanly? And just getting practice with that. So for example, you could say, well, I only traverse an edge after I mark a vertex. That you can see directly from the code. And then it's also easy to see that you only mark each vertex once. And then you conclude, oh, I only traverse each edge once. Yeah, so just 3 simple sentences. Nothing special. Okay, so that's the running time. So the marking is, of course, saving redundant effort. All right, how about this one? This is a statement, at least after the demo, you probably totally believe. The claim is that V is going to visit every vertex that's reachable from V. Okay, and in your mind, you're thinking something like, oh, it was traversing all the paths or something like this, right? Although the marking is intercepting some stuff, so it's a little bit awkward. So the question is just, how do we articulate something that maybe we all already believe, but it's still an exercise to try to prove something cleanly? Any ideas? You can ignore the A and B. Of course, there's some proof set up, but maybe it's more fun to first give it a try. Yeah,
Maybe like you do contradiction
okay.
and suppose that there's a vertex reachable from V that is not considered by DFS.
Okay.
That means at some point, there's like an intermediate edge that like you fail to take. And then I guess just like looking at the DFS algorithm.
Okay, so let me just say it out loud again. So, okay, suppose by contradiction there's a vertex that's reachable from V but wasn't marked, wasn't visited. And then the suggestion was like, well, and you can like imagine the algorithm, right? It's like, well, something went wrong. There must have been some intermediate edge that maybe was marked, but you didn't take the right edge or something like this. And then beyond that, it was something like, and if you look at the algorithm, that doesn't make sense or something, right? So even then, you could tell by the end, okay, we had the idea, but it would just like a little, to fall back and just end up saying, well, if you look at the algorithm, isn't it obvious? Okay, then we're just punting. We're not really doing the task. But so in other words, I think we all are fixated on there must be some mistake somewhere in the middle. And the only question is, how can we kind of articulate, make explicit that mistake? A proof by contradiction is fine. How can I sort of figure out how to express this idea of like some intermediate vertex? Yeah.
Like, let there be reachable vertex, some set S, be like T, and then if T is reachable from B, then and B is not T, then some neighbor of B must reach T. Like that.
Yeah, I mean, yeah. If you end your proof with something like that, yeah, you want to give it a try?
So if there is an intermediate vertex, like if we were going to go with a contradiction, where S is reachable from V
Sure.
and T is reachable from S, but T is not reachable from V, that's not possible. So like that's a contradiction.
Yes, but then that's definitely true. If V can reach S and S can reach T, then S must be able to reach T by definition of reachability. But I feel like that's talking more about the definition of reachability than what the algorithm is doing, right? There's something about marking and stuff going on. Somehow we're also asking like, are we sure marking doesn't mess anything up, right? Yeah.
Just try making articles is strong and saying the article and the includes example what we just visited. And then if it's still reachable, then that means it's
Okay, no, this is interesting. Well, I'm going to encourage it because I like all things recursive spec. Okay, so can we make our recursive spec stronger? So if I write like DFS of V,
and we can see that if there is no recursive spec, but this time we can say that we're not revisiting the previous.
Okay, so this will uh, visit all vertices reachable from V without revisiting V. Okay. Which indeed is kind of what we're implementing. I mean, there's a little bit of, oh, there's small things like the fact that you're not revisiting other vertices too, but there's also like, we still have to prove that the algorithm we implemented satisfies the recursive spec, I think, in this case.
Can we do something like, say, if there is a vertex that is not marked, but like we can travel from V to that vertex? So let's say, suppose that like it is not marked, so consider like a path that travel from V to the vertex. That means that all the vertex that can travel to like a vertex that's not marked is also not marked. Yeah.
Okay, so that was long and there was a lot of marked and unmarked, so it might have been confusing. But I think that the one nice idea that came out of it is like, okay, let's say S can reach T, there's some path, right? So just saying, oh, there is some path gives you something a little bit concrete to work with, right? Because your goal is to articulate this awkward intermediate vertex that for some reason you visited but didn't explore or something, right? So you could do something where once you presuppose there is a path because that follows from the definition of reachability, then you say, well, walk around on this path, find the first vertex that's marked, but the next vertex isn't or something, right? Then you can start pinpointing. So if you presuppose, oh, there must be a path, then you have something a little bit more concrete to work with. And then you can maybe articulate this idea we all have in mind about this bad vertex somewhere in the middle. Yeah.
Similar kind of idea. So assume that there is let target vertex T be reachable from V but be unmarked.
Yeah.
About remain unmarked. That means that even though there is intermediate vertex W, which we have marked, but we did not traverse the edge from W to T, then for that, then if you use we did not traverse that edge, well, because we traverse that edge, which means that the problem must be upstream, and you kind of just reverse that edge. W is marked, and we have to reach it, and we would traverse that edge, which means that W must be unmarked, which means that we have to go back to the W from V, and we just kind of like reversely get back. It's like we would have to traverse this path, and therefore our W is marked, and T is not, is wrong, and so we did mark T.
That's probably kind of okay, but it felt a little loopy. But I think one thing that's going on that you guys might have trouble articulating with is, okay, you have some unmarked T, you're supposed to mark it. And then you're like, well, there must be some previous neighbor that maybe was marked but didn't traverse the edge. Except it's quite possible that there's a whole bunch of vertices you didn't mark, right? And you keep going back and back and back. And then you start saying things like the word just. If you use the word just a lot in your proof, that's not a good sign. But then another is like, oh, I didn't recursively, but okay. So here's one way to just get it down. So at least I think we appreciate like the awkwardness of it all. So for example, one thing you can do, and there's different ways to do this, is let me just first call A the set of vertices that are marked and B the vertices that are unmarked. Okay, and you just set up a little scaffolding and it'll make it easier to articulate all the things that you really completely understand. And let W be reachable from V, and suppose by contradiction, W is not reachable from, or wasn't marked. Okay, so W is in B, that's our contradiction. And now I think we're gonna go back to this path idea. So you have some set A of things that were marked and some set B that was unmarked, right? And all you know about W is that there's some path from V to W. So I'll draw a path like this, I'll make a crossover just to be interesting, right? Now, all I know about this path is it starts in A and it ends in B, right? So in particular, that tells you there's an existence of something went wrong, but you can pinpoint it now in this picture. What is that? Yeah.
The path that we traverse has to all be A.
Yeah, it has to all be A, or I guess the way I framed it is, at some level, the path hops over from A to B. right? So there was some vertex, sorry, I used lowercase a and lowercase b just to make it confusing. There was some vertex that I marked, and then proceeding vertex along the path I didn't mark. Okay, so once you kind of draw this up, okay, just because you cross over, there must be some crossover point. Now you pinpoint that crossover point. That's an intermediate vertex we kept alluding to. Right, that was sort of implicit in this idea of fix a path and then crawl up the path would be an alternative. And then once all this is set up, then you just have a sentence like, you know, since the path starts in A and ends in B, there must be some directed edge from some A and A to some B and B. Now you can look at the code and say, well, every time I mark a vertex, I explore all its edges and mark all those neighbors. That's where my contradiction is. Okay. All right, so I think we're proving something that we all sensed was correct, but this is just one way to get it down. So I'm not sure what the high level takeaway, maybe just sometimes just scaffolding, like setting up those sets A, setting up those sets B. If you just take it easy and define some things, then the punchline can get really easy. If you try to do it in one breath, then you find yourself telling like a very long sentence and it's like a snake eating its own tail or something, like it just goes on and on and on. And you're like, oh, how do I get out of this sentence? Right? So sometimes if you just go slow, set it up slowly, then it's not so bad. Okay, good. Fine. So those are our maybe our two claims that we'll work with. And I think I'll do something a little bit stronger. I mean, it'll be helpful to think in these terms, that DFS-V will only return after all the vertices reachable from V have been marked. Okay? It's just good to be in terms of marking. Okay. All right, so much for DFS. I think now, oh, what's here? We'll find out. Oh, maybe nothing is here. Okay, that's fine. Okay, so are we okay with these three things? Yeah.
Are these claims that we can just cite, say we know it is known that DFS reaches all?
Yeah, from now on, we can cite it forever. So in general, anything that's like a lemma theorem in a book, you can just cite. We don't have to reprove things. In fact, I encourage you to think of the, to think in terms of, you know, understand what the algorithm does so that you can use it in new ways instead of trying to change the algorithm. And then if you do change the algorithm, then you got to start proving stuff. But I think a lot of the goals in this class is try to conceptualize these things, right? Figure out what's going on at a more conceptual property level, and then think about how to manipulate that, okay? Instead of just always kind of brute forcing, writing a lot of new code, if that makes sense. But, well, it'll be drilled in one way or another, so. All right, but it's gonna come up soon. All right, so this brings us to part 3, which, well, let's see. Okay, so, all right, so we did this at the beginning, you know, topologically sorting DAGs. And I think we did the most natural thing, which was just to remove sources, remove source, remove source, remove source. Okay. And, okay, now, I want to put that in contrast or put that side by side with what we learned about DFS, right? So between the time that I mark V, I enter V and I mark it, and I go around, I crawl the graph, and then I exit DFS-V eventually, we're only marking and searching vertices that are reachable from V. So we also mark all the vertices reachable from V, but we also are restricted because we're always following some path in the graph. Okay, so now, okay, here's a claim. Okay, suppose I have two vertices where V can reach W, but W cannot reach V. Okay, so, you know, okay, fine. The claim, this might seem obvious, but then it's another like, oh, look, can we articulate it? If DFS explores both V and W, okay? And this can be non-trivial because your DFS might start somewhere else, right? It's visiting V and visiting W and stuff like this, okay? So you start your DFS somewhere else, but let's say somehow it visits both V and W. The claim is that it'll finish DFS on W before it finishes DFS of V. Okay, so I'm here. We're kind of really looking into like the order, some implicit ordering in the DFS. Okay, so, and it's somewhat general, right? I don't want to presuppose that I'm necessarily starting the DFS at V or anything like this. I'm just starting a DFS from somewhere. All I know is it visits both of these vertices, which have this relationship where V can reach W, but W cannot reach V. Not necessarily in a DAG either, just in a general graph. Okay, the claim is, okay, so it does visit V at some point, it does visit W at some point, but the claim is that whatever happens, it'll finish W before it finishes V. Okay. Anyone want to take a whack at it? Yeah.
We can do this by cases, so we can say, okay, if the path reaches V first, and then we're looking at that case that reaches V first, and then we can look at the case that reaches W first.
Okay, perfect. Okay, so case one, case two. Case one, DFS marks V first. Case two, it marks W first. Okay, so if it marks V first, then what would I say? You just said it, but maybe say it again.
So
Yeah.
we go to W.
Yeah, so we can kind of rely on this property. You know, once it marks V, then we already know that it's going to go and mark W just from the properties we already know from DFSV. And finish DFSW before it finishes DFSV. Okay. All right. The next one, what if it marks W first? Then here, since we know DFSW only searches the vertices reachable from W, which excludes V by hypothesis, it'll finish DFSW before it ever gets to V. Okay, nothing too simple. If we had struggled more as a class, then I would make a big deal about breaking into cases. Okay, but you got it right away. So, all right, but simple enough. Okay. So now consider an ordering like this. Suppose as I ran DFS, okay, as I exited a vertex, I finished searching that vertex, I appended it to the output. Okay, so I'm just logging things as I finish searching them. And of course, you know, you might not end up visiting all of the vertices. So I'm going to wrap it in just a simple loop. You know, you might call it a driver, but I'll just call DFS on every vertex. If I've already visited that vertex, it'll just exit right away, nothing special. Okay, but this will make sure we visit everyone. Another way to think about that is like, another way to think of this post DFS driver is like, imagine you had some crazy graph. The driver is sort of like adding a special vertex that has an edge to everyone and running DFS from this special vertex that can reach everyone. Then that first step will be looping over all the vertices. That's another way to think about it. Okay. All right. Now, I want to think about what happens on DAGs. So first of all, not a trick question. If you can reach V, then V cannot reach you. Why? Yeah, because that would be a cycle. That would induce a cycle. Okay. So you have this thing. And so that means that this post DFS is always going to print V before U. Okay, so based on what we just did, if U can reach V, then V cannot reach U. So that means that we'll always finish V before U. That previous lemma we just did, we broke into two cases. I think I might have switched U and V, which is maybe making it confusing. But if U can reach V and V cannot reach U, then you know that DFS will always print out V before U. It will always finish DFS on V before it finishes U. So if I printed them out, right, all the reachability has to go in this direction. Okay? So it always has to go from right to left. And so what is this basically? It's a topological order, except it's in reverse. So if you ran post DFS on a graph and put in a driver, that's another way to print out a topological order. It's a little bit more counterintuitive, I think, than just pulling out sources. Okay. But it also helps you understand. I think it's more to understand what DFS is doing than what topological ordering is. Okay. Yeah. So obviously it's reversed. So once you print it out, you can just flip it over. Alternatively, if you wanted it to originally print out in topological order, what could you do?
Right before the school.
Oh, print before. I'm not sure actually about that. Yeah.
In the graph and then do it.
Yeah, we can flip the edges in the graph and then do it. So that's always another option to keep in mind. Okay, good. That's fine. So DFS plus reversing either before or after will give you another linear time algorithm for topological ordering. A harder algorithm maybe, but another algorithm. Okay, good. So I think this brings us to kind of the last leg. Has to do with something called strongly connected components. So what we just did was for DAGs. Now let's remove that. So I'll say that two vertices are strongly connected if they can reach each other. There's a path from S to T, and there's a path from T to S. Okay? And a graph is strongly connected if every pair of vertices is strongly connected. All right, so good. Okay, so the fancy word is that stronger connectivity defines an equivalence class, which is say like if A and B are strongly connected and B and C are strongly connected, then A and C are also strongly connected. All right, let's just prove that very quickly. Maybe it's not too surprising. So here, let's suppose that U and V are strongly connected and V and W are strongly connected. Why now are U and W strongly connected? Yeah.
If they're an equivalence class, then by transitivity, if you can reach B and if you can reach W.
Yeah. I would frame it only slightly differently because we're proving that it's transitive and we're proving that it's an equivalence class. But yeah, you said the key thing. You know, if you can reach V and V can reach W, you should be able to concatenate those walks so that U can get to W. And vice versa, if W can reach V and V can reach U, the fancy word is transitive, but all that's really going on is you concatenate these walks through the graph, you'll get a walk from W to U. So we're just concatenating, nothing special. Okay. But in that sense, they form an equivalence class. So that will partition all of the vertices. Okay. So each of these equivalence classes in a given graph is called a strongly connected component. Okay, so I've taken that graph that we had before and I've divided it by color into a strongly connected components. So down here we have these two vertices, they're sinks, they can't reach anyone. So they're just in a strongly connected component by itself. That triangle that we found before, that's a strongly connected component. It can reach some other vertices, but those other vertices can't reach it. We have this triangle on the left, and then we have another strongly connected, the bigger one in the top right. Okay, and they partition the vertices. If you had a vertex sitting in two strongly connected components, why would that be a contradiction? Then all those vertices in either component can reach each other via this vertex. So they would be merged. Okay, so strongly connected components, like equivalence classes, always have this kind of maximality, partition property about them. Okay, so that's one nice way to decompose a graph. So our goal ultimately is to take a graph and figure out all the strongly connected components of the graph, and we'll try to do it as fast as possible. But first we'll just start as a warm-up with one vertex. Okay? Suppose I have some vertex V, and I just want to find a strongly connected component. So everyone it can reach and can reach it simultaneously. Okay, any proposals for an algorithm to compute the strongly connected component of a given vertex V? Yeah.
Run DFS from V.
Okay.
DFS on the graph, all the edges reverse, starting at V that we can provide.
Okay. Well, you cut to the point really fast. So usually, other suggestions come up first. That is indeed what we'll do. A more naive thing is first run DFS from V, and then run DFS from every other vertex to see who can reach V. Okay, and then you're running n DFSs, so it would take like m times n time. Okay, but this solution is more clever. Okay, yeah, well, yeah, you just totally spoiled it, but that's okay. All right, so the naive thing would take is not that fast because you would run DFS from every vertex just to figure out who can reach V. It would be correct, but it's not as fast as we would like. The suggested solution was more clever. If I want to figure out who can reach V, let's first reverse all the edges in the graph, okay? And then run DFS from V in the reverse graph, okay? So if a vertex A can reach V originally, once I reverse the edges, then V can reach A. And that's like an if and only if. Okay? So if you do this, instead of having to run DFS from everyone, you're just running DFS from V twice. Okay? And you only have to do 2 depth first search instead of n. Okay, so that's a big win. So once you do 2 DFSs, then you just look at who was marked in both of them, and you just combine the lists. Okay, good. So that, okay, but the real moral, which I feel like is not as dramatic because you guessed it right away, is, okay, yeah, another like complicated idea that's often suggested is like, imagine you're doing depth first search from V and you're like building out this tree and then you find a back edge and you try to collapse that cycle and then you keep going and then back, there's like some crazy back edge solution that no one ever understands, but that's often proposed. In any case, whether or not that works, that's clearly quite complicated, right? But it's quite tempting to just go in and change the algorithm because you can kind of visualize it, you can kind of see it, maybe it'll work, I don't know, right? But if you instead don't worry about changing the algorithm, you understand how DFS works, you know what it does, you can just change the input. It's much easier to reason about DFS running on the reverse graph than any incredibly complicated algorithm working with back edges and collapsing trees and somehow you're hoping that your marks are still okay and all this stuff. Yeah.
How difficult is it, like time complexity wise, to reverse the graph?
Yeah.
Like we sorted out.
How hard would it be to reverse the graph? Let's say you had an adjacency list representation. Yeah.
Is it,
Yeah, you can just go through all the lists and rebuild the list. That'll be linear time. You're already spending linear time on depth first search. I guess if you're like really clever, you can take your adjacency list data structure and add a flag called like reversed. And then you interpret all your in lists as out lists and all your out lists as in lists or something. Then it's like 01 or something. But in any case, it's just one pass through the data, so it's not a bottleneck. So the big O notation is your friend. You can just do lazy stuff and just focus on it being clear and correct and getting the right asymptotics, getting the right concepts. You don't have to worry as much about some of the details. Okay, we're gonna be okay. All right, so I guess we've already kind of implicitly done this, but the running time would be m plus n here, including the time to reverse the graph. Maybe on to just combine the 2 lists, because it's just 2 lists of vertices. You add that all up, you get m plus n. Okay, good. Now, all right, so here comes the next stage. If you wanted to get all the strongly connected components, to get that decomposition, we could do what we do and apply it from every vertex. Okay, but that'll still take n times m plus n time. We could even more naively just run DFS from everywhere and then kind of looked at the results of all of these and see kind of who occurs with each other, if that makes sense. We don't even need this reversal trick if our only goal is mn time. Okay, so our goal now is to try to beat mn. Okay. All right, so here's maybe a conceptual point I want to make. So here's that graph from before where I've color-coded strongly connected components. Now imagine taking every strongly connected component and contracting it into a single vertex. Okay, so you can kind of see like the outline of the small, contracted graph. And so, because there's at least one edge going out from green to this red dot, there's still an edge left in this graph. So you just identify all the vertices and then the edges still stay in there. It's possible that some edges should be duplicated. I didn't draw out the duplicates because we're doing reachability, so multiplicity doesn't matter too much. But right, so you can contract the vertices and you get this kind of like contracted subgraph. Okay, does that operation make sense? Okay, and it'll take m plus n time to just identify things. Not a big deal. Okay, now compared to this graph, there's something conspicuous about this graph. There's something nice about this graph. Yeah,
It's a jag.
it's a DAG. There's no cycles. Why are there no cycles? You collapse all the cycles. If there was a cycle, I don't know, between the top three, that would make them all mutually reachable with each other and you would contract that again. Okay, so you're left with a DAG. Okay, and so we're going to try to somehow take advantage of this implicit, there's always a DAG of strongly connected components. Also, when it comes up on the homework, you can assume you have a subroutine that gives you this DAG of strongly connected components. Now, right, so there's no cycles, it's a DAG. Now, our current approach to computing the strongly connected components is just to get naively Mn, pick any vertex V, get a strongly connected component, rip it out of the graph. Seems like a natural thing to do. And that'll give you something like Mn time because you're spending M time to get each strongly connected component. Here, I'm assuming M is at least N, which is often the case, just to make my notation easier. Okay, now, okay, so how would I pose this? Okay, so right now, we don't know much about the graph, so we can choose any vertex. And what else can we do? But maybe suspend that. If you could choose somehow, what would be like the best vertex to pick in each iteration? Yeah.
Highest out degree.
With what?
Highest
Oh,
out.
highest out degree. So highest out degree, if I pick like this one, a vertex in here, then you would explore a lot of the graph. Or maybe if I pick this one, you would explore the whole graph. Okay. Yeah. Any other suggestions? We're going to do actually something kind of almost the opposite. So suppose this. Suppose, like if I could pick any vertex I wanted to make this algorithm really fast. Of course, it's cheating. We'll eventually figure out how to do this implicitly. Okay. If I had picked this vertex first, right? And if I knew it was from a sinc component, how can I get the strongly connected component of that vertex? I mean, you could do what we did, which is search everyone it can reach and then do the reverse search. But if you know it's in a sinc component, it can actually be simpler. Yeah.
Just run DFS and see what it and everything you visit is manufacturing.
Yeah, so if we just think about what sync component means, if here this is maybe trivial, so I'll move up to a more interesting one in a moment. But if I ran DFS from that vertex, it will visit everyone it can reach. But because it's in a sync component, it won't leave the component. So it won't accidentally reach anyone it's not supposed to reach, so to speak. Right? So you could even get away with like one DFS if you could just pick the right vertex. You don't even have to reverse anymore, right? So if you could do that, you could say, okay, I figured out this strongly connected component, and I'll just rip it out of the graph. And my strongly connected component thing would update like this. Maybe that's not so interesting because there's only one vertex. But now we have like a sync component that actually has a few vertices. Right? Suppose I did one of these vertices next. So if this was the second vertex I visited, right? That first search is going to go here, and it's going to go here, right? And then it's only going to search that component, and it's not going to be able to escape because at this point, it's a sync component. That's what sync component means. So if I had picked a vertex from that component, then I could just search that, never leave it, and I would just get the whole strongly connected component. Obviously, how are we going to choose that vertex? That's momentarily, okay? But that's the strategy, right? If I could keep picking vertices from sync components, something like this, and then I guess I shouldn't have erased it. Something like this will come next. Something like this, that'll erase this thing. And then I pick maybe one of the yellow ones, and that'll gobble up all of these yellow vertices. I wish I hadn't erased the purple edges, but oh well. Right? And then gradually you're whittling away at the graph, right? So if you could get the sync components, then you could actually do this quite fast because your depth first search over all the searches only visits each vertex once. There's no redundancy. So although in the worst case, the depth first search could take m plus n time, if you look carefully, you're only looking at each edge once total over all of these. So the whole thing would come out to m plus n if you could only pick the right vertex every time. Okay, but that's the strategy. So that's what we want to try to do. If we can somehow do some kind of sync first strongly connected component, we don't know how to pick that vertex yet, we would suddenly get an incredibly fast algorithm, right? M plus n time, you're only looking at the graph once. Can't expect anything better. Okay. Now, okay, so that's the idea. That's just some sync force memory. Okay. So if we can figure out the sync components on the fly, then we get m plus n time. And I'll go a little faster because we're basically out of time. Now, okay, I think there's only one rhetorical moment left. So remember, we saw that post-order DFS will actually sort of list the vertices in sync first order if it's a DAG. Okay, that would be nice. Now, in a graph, so if I actually ran depth first search on that graph, this is one possible output. Okay, so on a DAG, it will put the sync first. But what do you notice about this? So that graph is not a DAG, and this vertex in particular, it's not a sync. Okay, so it's actually not a sync. So running depth first search isn't going to quite get what we get. It is true on a DAG, it'll output the syncs first, but not necessarily on a normal graph. So this is completely a plausible thing. That said, all the blue edges do go from right to left. So if you had kind of like, so some level, if you just like look at the components where you kind of identify the colors, the arrows are going, you know, the right direction. Okay. Okay. Now, okay. So actually, the last vertex isn't going to quite work, but I should make sure we're making progress here. Okay. So, okay. What about the first vertex? So the first vertex is actually from a source component. Okay, and that's actually always going to be, or last vertex. I get confused. The last vertex is going to be from a source component. So if I listed these vertices in order as printed by PostDFS, you're always going to get that the last vertex is from the source component. Okay, that kind of follows from what we did before. I won't belabor it too much in the interest of time. Let's just take this for granted for the moment so we can finish off. Okay, so PostDFS won't do exactly what you wanted, which is to give you the sync component. It does have some nice properties though. PostDFS will always put a source or vertex from a source component last. But you're really looking for things in the sync. Okay, so now what? Yeah? We're just going to reverse the edges, then do a post-DFS order on the reverse graph. And now things in the sync component are going to be at sync component of your original graph, source component of your reverse graph are going to appear at the end. Another nice thing is that once you erase some of this stuff, you'll still have a post-DFS order of the remaining graph. Okay, so you only have to do this once, and then you can just peel off. Okay, so here then is the final algorithm, and we're basically done. You do a post-DFS ordering of the reverse graph, assuming we've established that that last vertex is already always from a source component. Then you can always pick V to be the last vertex in that ordering you computed at first. So you just take the last vertex, it's going to be in a sync component in the original graph, and then you can run your strongly connected, DFS from that vertex, and you rip out a component. Okay? And even after you rip it out, you still have a post-DFS remaining, so that next last vertex will still be from a sync component. Okay? So that's it. So that's this whole, most magical algorithm in the class. If you actually process the vertices in a particular order given by DFS, then you can rip out the chunks, the S strongly connected components one at a time with no redundancy and pull out the entire strongly connected component structure in linear time. Okay. And on homework, if that comes up, you can use that as a black box as well. All right. Sounds good. Thank you.